Hello students, so we had discussed about this op-amp performance parameter in the last class, and we will be continuing few more parameters. Let me just collect it. Yeah. So the very two parameters that we have discussed is about the gain, and later we discussed about the small signal bandwidth, and the third parameter that we are going to discuss today is the large signal performance parameter. Okay, so again, this large signal performance parameter is something that whenever an op amp deals with a large input signal, uh, the op amp cannot able to sustain such a large input signal to it. Okay, so it is something like you have an op amp that has been built by using some technology, and there is some sort of minimum input that this op amp can accept, so that one could model this op amp as a linear circuit. Okay. But the moment if the step input goes high, then to a large value, like say for example 2 volt or 3 volt, and provided this op amp is operated between the power supply of 1 volt, then what possibly can happen is that this op amp is no more considered as a linear circuit, and this circuit becomes a non-linear. Okay. So it gets switched from linear circuit to a non-linear circuit, and one cannot use this small signal bandwidth. So whatever the concept that we have learned in the previous parameter cannot be applied in the computation of the large signal performance. Okay, so we need to completely get into a different perspective of this particular op amp. Okay, so what I really mean is that then just because of the nonlinear phenomena that gets into this op amp when we apply a large step input, uh, and due to which the analysis becomes too complicated. Okay, and one cannot characterize the speed of this op amp just by looking at the small signal bandwidth. So this is no more applicable, because we calculated the small signal bandwidth based on the linear, based on the assumption that this op amp is operated, or yeah, operated as a linear circuit. Okay, so so this particular phenomena we'll just discuss when we discuss about the sleeve rate phenomena. So how to deal or how to work out this op amp when we apply a large step input, and how to compute the sleeve rate based on that analysis. Okay, yeah. So the fourth parameter that we will be concentrating here today would be the input common mode range, and I'll just try to discuss about this with a kind of circuit setup that is shown here. Okay, so this is nothing but it's a kind of closed loop unity gain amplifier, and so the moment we have this kind of connection, this kind of feedback connection, let us try to compute what is the range of or what is the input common mode range that we end up having for this particular circuit. Okay, so just a second. Yeah, so I'm just ensuring that there is no disturbance from the other end of. Yeah. So, so first of all, one has to know what is the common mode input common mode range when this op amp is in open circuit configuration. So, what does it mean is that if I don't have this loop, okay, let me just use this. So, this is my feedback path that connects the output, which is here, V out, that is connected back to the input, which is here, and that has been reflected to the gate of this M2. Okay, so if I could able to break this particular loop, then we would end up having a kind of uh, differential pair which looks something like this, right? So, and these are the concepts that we have discussed already, so it is just a quick revision that I am trying to make here, and if you still have any sort of doubts, we can discuss in the WebEx. Okay. So this is our M3, M4, and here I'm tapping my output, and right now there is no feedback here. but since because I need to apply a common mode input, I have to attach both those M1 and M2 gate terminals and then apply to some sort of common potential, which I label it as VICM. Okay, yeah. So now, what is the maximum value that VICM has to have, and what is the minimum value that one has to have, such that uh, all of these four transistors, and if I replace this ISS, there is the tail current source, with again one more transistor, then even this tail current been implemented by a kind of transistor that has been biased in saturation also has to retain in the saturation regime whenever we have the highest value or whenever this VICM has the minimum value. Okay. Now let us try to compute what is the maximum and the minimum value of this common mode input when we don't have any feedback. Okay, and later we'll just get back to this, trying to compute the what happens to those common mode range when we had this kind of uh, feedback circuit where beta is equal to 1 in this case. Okay, yeah. So now let us begin with the computation of common mode range for a open loop differential pair. Now in this case we know that there is a minimum voltage that we need to maintain across this gate and source, and that minimum voltage has to be proportional to the current that is flowing through the circuit, right? And the currents that would flow through the circuit would be half the value of this ISS in both these branches. Now in order to draw such current, we have to have some VGS here for both M1 and M2 transistors, and that if I label it as VGS1, and over here I will label it as VGS2. So those are the minimum voltages I have to apply across the gate and source such that it draws the current of ISS by 2 here. And also if at all, if I if I realize this ISS with a kind of a single NMOS transistor between the drain and the source. So what I really mean is that say for example, I am just using M5 here in the place of ISS, and I have just fixed some bias voltage such that this particular transistor M5 is operated in saturation regime. Now what is the minimum voltage that I need to maintain across the drain and the source is that it can be returned as the VOV 5, right? Yeah. So now let us try to utilize all these data in order to write down the input common mode range, the minimum value of it. Okay. So the minimum value that I need to maintain across the gate and source is written as VGS1, and since because both these transistors M1 and M2 are assumed to be the same aspect ratio, I would write it as VGS1 comma 2, okay, as a common term, plus the voltage drop across the drain and source of M5, which is supposed to have a minimum voltage of VOV, otherwise the transistor will get into linear region. Okay, yeah. So this is the minimum voltage that I need to apply when we have a open loop configuration. Now let us try to identify what is the maximum voltage that this potential can have. So in order to read out the maximum potential, one has to quickly recall what are the things that we need to consider when we consider about the drain of M1 and M2, right? Yeah. So now here in this case, let us assume that this particular node potential is equal to Vx, and we also have discussed uh, the analysis, like what potential that one will have across this particular node V out when like through some sort of contradiction. Okay, so hope that you remember those principles. Okay, now in that case, uh, through contradiction we have proved that both these nodes, the drain of M1 as well as the drain of M2, should have the same potential if the input that is being applied is a common mode input. Okay, so this is something that we have already discussed, and I am just trying to recall and make sure that you understand this. Okay, uh, not receiving enough. Yeah, I think I am getting some message stating that the video is lagging. I'm not sure about it. If others also have the same sort of issue, you can just text me so that I'll just try to cut the view and like I'll stop the stream and then I'll restream again. Okay, so till then I'll just try to continue my session. So here in this case, let us try to compute that. So we know that in order to have the same current across both these branches, which is ISS by 2 in both the branches, one has to have the Vx to be exactly equal to our Vout, or Vout is basically equal to Vx. Okay, so that is the norm that we have already discussed. And now let us try to compute the value of this Vx. Now, in case if this source of M3 and M5 is connected to VDD, then one could write the potential of this node X as something like VDD minus the VGS3. Okay. Now, in case if I assume that the W by L factors of M3 and M4 are same, it's supposed to be equal. Yeah. So, if they are equal, then this node V out will also carries the same potential of VDD minus VGS4, and ensure that you put a modulus across this VGS just because it's a PMOS device, and we are talking about the DC conditions here. It's not a kind of AC conditions here. Okay. So, based on this, we got the potential, the drain potential of this M1 and M2. Now, we know that whenever we want to have a transistor in the saturation regime, the we have a condition stating that for an NMOS, the VDS has to be greater than or at least equal to VGS minus VT. Okay. So, again one could cancel out these source potentials just by writing VDS as VD minus VS and VGS as VG minus VS. So, there is a potential which is common to both the sides, so which we can cancel it, and what we have is something like talking in terms of drain and the gate, leaving out our source potential. Okay. So, now the minimum voltage that I need to have across the drain would then be returned as Vg minus Vt. Okay. So, now what is connected to my Vg is nothing but my VICM. So, I could replace this Vg with VICM, and in a way I could write that it's supposed to be equal to Vd plus Vt. Okay. So, this Vt is being shifted towards the left and being added along with the size of Vt. So, based on this, one could write that the input, sorry, the input common mode range, the maximum range that one has to apply in order to make sure that all of the transistors are staying in saturation, can be returned as something like VDD minus VGS 3,4 plus VT. Okay. So, these are the minimum and the maximum range of common mode voltage that we have when the circuit is open circuited. Okay. So, it is under the open circuit condition range. Okay. So, now let me just try to remove these contents here. Yeah. So, now when we have this connection of feedback around this drain of M2 and the gate of M2, now let us try to evaluate the same sort of computation and see whether there is any change in those common mode ranges. Okay. Now, in this case, we have this input common mode range could be returned as V in max. Okay. So, I am just writing in terms of this potential. Okay. And that is nothing but we have to have again the same voltage drop across it. So, due to which it can be written as VGS1, and we also have to maintain the potential drop across this current source ISS, and if at all if I assume that this is being replaced with an NMOS transistor, then the minimum drop would then be returned as something like VOV of the current source. So, rather than writing it as M5 here, I will write it as CS just to replicate that it is it's again the VOV in the place of ISS. Okay. And even if we look back into the V in max condition, sorry, this is the top one is V in minimum condition, sorry for that. Yeah. So, for the V in max condition, again it is something like the drain potential plus the threshold voltage of transistor M1, and once again when we look for this drain potential, it is equal to VDD minus VGS3 plus VTH1. Okay. Yeah. So, as you could able to see that there is no change between this open circuit condition as well as in the closed loop circuit condition. Okay. So, there is no change even here. Okay. Now the reason you might wonder that since because the gate and the drains are being shorted, how could I write it? Okay, so like how could I relate this with only with respect to the VD1 and not with respect to VD2? The reason for this is that as I said, the V out ha- has to have the potential of Vx. Okay, but this is something like V out can follow the potential of Vx, but Vx no need to follow the potential of V out. Okay, so that is something that we have discussed during the class session. So it is only the V out can follow. Okay, sorry, the Vx can dictate. So this is something like dictate the potential of V out, but the other way around is not possible. That is, V out cannot dictate the potential of Vx. Okay, so this is something that we always have to have in our mind, and that is the reason why we could write this particular expression and expand this expression of Vd1 as something like this. Okay, yeah. So now based on this, we could see finally that the open circuit condition of this input common mode range as well as the closed loop condition of this input common mode range. Okay, I have got another message stating that it's not audible. Okay, let me just try to connect my mic a bit closer. So hope that right now it is clear. So in case if you still have some sort of issue, please type in the message. So I'll just see that. Yeah. So now based on this given values, let us try to plug in these quantities, and then later we'll just try to compute what is the input common mode range of this particular setup, provided if this op amp is replaced with this simple differential pair. Okay, yeah. So now in this case, let us try to compute what is our V in minimum. So in order to compute the V in minimum, what we wanted is the value of this VGS 1. Okay, but what is given in the question is VOV and the value of VT, and we know that the value of VOV is expressed as VGS minus VT, right? From this, one could evaluate the value of this VGS as the summation of VOV plus VT. So when I try to add these two quantities, I would get the value of this VOV. And for all the transistors that are given in the circuit, the VOV and the VTH value would remain the same. And based on this, one could write this VGS1 as VOV plus VTH, which is equal to 1 plus the VCS or the drop across this current source ISS. Okay, so now as I said, even the drop across this current source is basically a VOV value, and due to which it can be added with 0.3, and that is the minimum drop that I have to maintain across the drain and source of ISS if this ISS has been replaced with some transistor. Okay, so based on this, one would end up having a value of 1.3 as its minimum input common mode value. Now let us move on to the next parameter, which is the input common mode maximum value, and that is returned as VDD minus VGS plus VDH. So this is a pretty simple process. So we know that the value of VDD is given as 3 volt. So let us substitute that. So it is 3 minus the VGS, which is equal to 1, and the the threshold voltage has a value of 0.7. Okay, so when we add them all together, we end up having a voltage or a kind of expression that is equal to, I think I have, yeah, exactly. So it is 2.7. Okay, so it is this 2.7 volt is the maximum voltage that we can have across this Vin. Okay, when we apply a common mode signal, or whenever we apply some sort of input signal, that is the maximum and the minimum range that we can have. Okay, so hope that you are clear with this. And now still we have to yet to compute the range. Okay, so what do we mean by the range or the input common mode range is this. Okay, so it is something like V in common mode range is written as V in max minus V in minimum. So the difference between the maximum and the minimum value will return as the range of it. Okay, so it is from here it is pretty much calculated that it is 2.7 is the maximum minus the minimum voltage which is 1.3, and that will return as a value which is equal to 1.4 volt as the swing range or the input common mode range that we can have across this particular circuit conditions. Okay, so now we'll just end up our discussion of parameters here. All of the parameters like linearity and noise and supply rejection ratio that I have listed in the last stream will be discussed as and when we discuss about a particular topic on it. Okay, yeah. So now we just move on to the next one, which is the, so again I have to have some space. Yeah. So now we'll just look across different circuit topologies that can be used in order to increase uh, the gain of the system, okay, or the gain of this op amp. And the reason for that, as I said earlier, when we go for lower technologies, the length of the channel decreases, and due to which the R naught in general gets reduced, and the total gain of the system also gets reduced due to that. Okay, yeah. So before I actually start this discussion, though, I just want to quickly recall few of the parameters that we will try to recall few of the parameters. Okay, so just a second, because there are a few pictures that I haven't copied it. Just for the quick review, I just want to bring some of the figures. Yeah. So these are actually not the circuit topologies that we are about to discuss. It is only the review that we are making, and based on this review, we'll just talk about the circuit topologies later. Okay, I just need a bit more space of it. Just try to push them down. Yeah. So now in this case, let us try to compute the output voltage swing and the gain of this circuit. And this type of circuit is also called as differential pairs, but the outputs are taken differentially. Okay, so yeah, so let us try to reason it why it is called as a differential output. But basically, we'll just try to work on a few of the parameters like the gain and the output swing that these circuits can deliver to us. Okay, yeah. So now, as we could able to see that this circuit seems to be symmetric, and just because it's a symmetric, one could actually take only one half of the circuit just by drawing a line of symmetry. And when we try to draw the line of symmetry, one could consider that this node uh, Vp, which we always tend to write this node as Vp, this node is driven to ground just because the circuit is symmetric, and when we apply an antisymmetrical input, this node Vp will go to the ground, right? And due to which one could analyze only one half of the circuit that is composed of M3 and M1 alone. And if we see carefully that this is nothing but it's a CS amplifier with a diode connected load. Okay, and one could quickly recall that the gain that we would get out of the circuit is written as GM 1 comma 2 and multiplied by the impedance. So it would be like 1 by GM3 in parallel with RO3. That is the top impedance that we would have when we look up, and when we look down, we end up having the drain. So due to which the drain impedance is nothing but our RO1. Okay, so hope that you remember all these concepts, right? Yeah. So even I can write a negative sign, but this is not a matter here, just because we are talking about a circuit which is observing the outputs differentially. Okay, so having those negative sign is not a big deal. So we will not follow this negative sign for the differential pass here. Okay, yeah. Now apart from this, let us even try to compute the gain of this B circuit that has been drawn here. So again, since the circuit is symmetric, one could analyze only one half of the circuit, and it seems to be that this circuit is nothing but the CS amplifier with a current source load, and due to which one could write the gain of this particular circuit as GM 1 comma 2, and the impedance is RO3 in parallel with RO1. Okay, yeah. So this is fine. These are with respect to the gain that we have written down, but now we just want to quickly talk about the output swing. Now this output swing is basically composed of two components. Basically, it is something like VO max and VO minimum. So let me try to compute this VO max and VO minimum for the circuit number A, and later we'll just try to evaluate the output swing based on these expressions that we have got for VO max and VO minimum. Okay, yeah. So now, since because the circuit is symmetric, if you are using only one half of the circuit to analyze your swing, then basically, yeah, there is something that we need to consider while considering the output swing. So even though the circuit seems to be symmetric, while evaluating the output swing, there is some caution has to be taken care. Okay, and I purposefully brought this particular circuit into this theoretical part is just to talk about few things. Okay, yeah. So let me try to concentrate on what we are actually working with this. Now let us try to compute the maximum output that I can have a swing around this particular node. Okay, so around this node X, and let me know mark the other end of the node as node Y. Okay, now so what is the maximum swing that it can have over this common mode voltage, and you know what is this common mode voltage that we will have across this particular node. I will not reveal here, but you know this quantity here, and over this common mode range